Hello everybody, my name is Iulia. I am currently working at Popen Associații in Bucharest, Romania as a design engineer, and I'm going to present you my research which is the evaluation of structural properties of high performance steel obtained on coupon specimens. The co-authors of this research are my professors from TU Delft and also our colleagues from ArcelorMittal Gandraj who provided the coupon specimens. I'm going to start with a short introduction to the subject. Then I'm going to present you a little bit of the research methodology that I used. Also about the experimental procedure and the evaluation of the results, leading to the final conclusion of the research. Our research aims to bring new knowledge about 3D printed material using wire and arc additive manufacturing. Also, this was one of the first times that carbon steel electrodes were used. For the elastic parts, the displacement rates that were used were of 0.015 mm per second, moving to yielding to fracture at the displacement rates of 0.375 mm per second at a photo frequency of 2 Hz. This means that a large amount of data had to be analyzed. I personally analyzed 35 gigabytes of data out of 120 gigabytes that were taken in total. Picture and roughness measurements. I had around 100 pictures for every test, and I had to filter photos using powerful scripts to reduce the time of the analysis. Regarding the experimental procedure, 8 mild and 14 raw specimens were analyzed. We used the smallest specimen that was available in order to cut as many specimens as we could from one plate. The specimens were cut perpendicular, inclined, and longitudinal to the printing direction, and in the pictures, the roughness shows the cutting direction, which is longitudinal, inclined here, and perpendicular to the printing direction. We analyzed mild and as printed specimens, cut in different directions from the plate, in order to inspect the geometric irregularities and anisotropic behavior of the material. The statistic protocol was made according to the American standard. For the measuring technology, we used digital image correlation, and to validate and calibrate the results, we used finite element method analysis. The final objective of this research is to find out material model for 3D printed materials using elastic plastic hardening and damage parameters. Regarding the stress-strain curves methods, the standard gauge length of 25 mm was used, and in GOM, I used two types of analysis, which is the facet point and the surface analysis. For both analysis, I defined 3 sets of points and the gauge length between them. 2 gauge lengths were on the edges of the specimen and 1 in the middle. Both types of analysis, the surface and the facet point analysis, provided similar results. Furthermore, I used the force that I obtained from the machine and the displacement that I obtained from the digital image correlation, transferred the displacement to strain by the gauge length, and ended up getting the stress-strain curves. For the stress-strain curves, I extracted 8 TUD characteristic points, which are the proportional limit, the yielding point, the start of the plastic behavior leading up to the ultimate strength and strain. Point F and G are 2 points that describe the post-necking behavior and leading up to the fracture strain. For the elastic material properties, I determined the E modulus, Poisson ratio, and yielding stress using a nominal stress range from 50 to 300 megapascals, and for the E modulus and Poisson ratio, the classic methods for determining the properties. For the yielding stress, I computed a 0.2% strain with the slope of the elastic modulus, and at the intersection of the 0.2% strain and the stress-strain curve, I found the yielding point. Finally, I obtained all the stress-strain curves for mild and also as printed specimens cut in the longitudinal, perpendicular, or inclined direction to the printing direction. They are very similar up until the ultimate strength, and after that they start to be a little bit different. To calibrate the material model, in the elastic stage, I introduced the E modulus Poisson ratio and density obtained from the test. In the plastic stage, I calculated the true stress and the true plastic strains, and then in the coupled plastic damage zone, I used the weighted average model, calibrating parameter W, the weight parameter, and parameter V that best describe the damage. In the coupled plastic damage, plastic dominated zone, the weighting factor W takes values between 0 and 1. I calibrated the weighting factor using finite element method. I calibrated 6 mild coupons, the minimum and the maximum for the tree cutting direction, which is perpendicular, longitudinal, and inclined. In the coupled plastic damage dominated zone, the weight parameter W is not enough to describe the damage evolution. Therefore, parameter B has to be calibrated again using the finite element method analysis. We can see that the stress strain curve from the test and also from the simulation agree very well up until the damage initiation point. Therefore, to calibrate parameter B, I searched for the sigma that was corresponding to damage initiation, and in Abacus I extracted the plastic equivalent strain. Furthermore, I obtained by this way, by calibrating, the B parameter for 6 tests for mild coupons, the maximum and the minimum, as I said before, for perpendicular, inclined, and longitudinal cutting direction regarding the printing direction of the plate. If we make a comparison between the finite method element analysis and the digital image correlation, the results are very similar. For this particular specimen, I got 6.1% plastic equivalent strain, and from the IC for the same specimen, I got 0.6% strain. The roughness of the material is a really important parameter that was crucial to our research. Even though first time we measured each and every raw specimen with a caliper, because we knew that roughness is going to be of crucial importance, we decided to scan with a 3D scanner all the raw specimens. For each raw specimen, 10 measurements were made, like in the picture in the top right corner, 5 measurements on one side of the specimen and 5 specimens on the other side of the specimen. From these measurements that were made with different positions for the scanner, I extracted firstly a roughness profile with the height and the length of the height of the roughness and the length of the measurement. I extracted each wave from the roughness profile and put them together, shifted them to 0, and extracted a 6-degree polynomial that best describes the roughness for just one measurement of one specimen. Furthermore, all these calculations were put together to extract a 6-degree polynomial that best describes the roughness for one type of specimen, one specimen. As you can see, the roughness is really small, it's just 0.2 millimeters on one side of the specimen, and the length of the measurement is 2 millimeters. This is almost close to nothing. Here on the top right, on the bottom right of the screen, I made a simulation in a 3D program with the roughness of the specimen. This is not in scale, this is 1 to 10. Because the roughness being that small, it wouldn't be visible at a 1-to-1 scale. These analyses that I used were furthermore used in another research made by me and my professors regarding the infliction of roughness on the material properties. In conclusion, the material that I analyzed provides excellent results, complying with the provisions by the Eurocode 3 for both as printed and milled specimens. Regarding the elastic modulus and the ultimate and yielding strength and strain, which leads us to think that this might be the material of the future and that we might hear of it soon on a daily basis. Thank you very much for your attention. I hope you enjoyed my presentation and me and my colleagues' work. And now I'm waiting for your questions.